In this section, we'll do a little review of the currents that flow in an ideal diode, and then generalize that to what we'll call a short diode, which means that instead of semi-infinite NNP regions, we'll have finite-sized NNP regions. And critically, it depends on the minority carrier diffusion length. So we can write the ambipolar transport equation for the injected minority carriers on both sides. So we're going to start there. Here's our p-n junction schematically. We have our depletion width here. And remember that if we put forward bias on this, we raise up the energy levels of this side, and we launch some majority electrons from this side, which travel by diffusion through the depletion width and arrive at the edge of the depletion width on the p-type side, where they become minority injected carriers. And this notation here means that it's the minority electrons on the p-type side that their concentration depends on the applied voltage on the junction. So for this section, I'm going to define a convenient axis x prime, which is going to run that way into the p-type side of the junction outside, starting at the depletion width edge, and then I'll use x for this side if we use it. So x prime equals 0 and x equals 0 are the boundaries of the depletion width. So in this section here, we can write the ambipolar diffusion equation as d squared delta n dx prime squared plus mu and e d delta n dx prime plus any generation minus thermal generation minus our recombination, and we're going to use the assumption of low injection and the lifetime approximation to allow us to simplify this here. And this is all equal to d delta n on the p-type side over d time. Okay, so we're assuming when we're deriving this JV curve that we're in steady state. So steady state tells us this goes away. Okay, we're assuming that we're in the dark, so this goes away. In the quasi-neutral region, or Q and R, the E field present is non-zero, but it's basically tiny, and you can show that the amount of voltage drop across this region, except in weird cases, is going to be negligible. Therefore, this goes away also. So we're left with these two terms. And this formulation is going to be used again and again because the p-n junction shows up, for example, in MOSFETs as well as JFETs. We're going to end up using this simplified version a lot. So we've got a double derivative minus the quantity itself over tau and naught equals 0. And we could write similarly we could write similarly for holes in the n-type quasi-neutral region also. So what we're going to define is a characteristic length scale. So we're going to define the minority carrier diffusion length equal to square root of the diffusion constant times the tau, the minority carrier lifetime of electrons in the p-type side. And this allows us to write the solutions to this equation. The general solution is going to be some constant times e to the negative x prime over square root ln plus b e to the positive x prime over square root ln. So sort of as we discussed last time, we get these decaying exponentials for the delta n as a function of distance. So we've got our general solution. Now we need to make it particular by applying the boundary conditions. Okay. So for the ideal case, our boundary conditions are that we have a certain amount of excess carriers injected, which is a function of voltage, and then very far away from the junction, in fact, all the way at x prime equals infinity, we have that. So we'll go over here. Boundary conditions here. Ideal case, so our delta n p at x prime equals infinity has to go to 0. So this means our np, which is of course the np naught plus delta n p has to go to np naught, far away from the junction. Now, in the case of what we would call a short diode, instead of being a semi-infinite region, now we have a case where the diode, the semiconductor material ends, and there's an interface here with, let's say, the metal contact. So what happens in this case? Well, it turns out that if you think about a perfect interface, you start injecting some minority carriers here, and they'll tend to pile up. And what would happen is you would get some steady state concentration. In fact, we can look at this solution and see that if we were not extracting any current out of this boundary, we would pile up carriers into here, and then they would eventually start recombining because we would get a large concentration of excess carriers, which would recombine quickly. So now if we let some current flow out of the contact, we'll establish some steady state equilibrium value, steady state constant with time value. Now, if we allow for this interface to have a recombination velocity, so the interface itself can have some defects and cause recombination, then this steady state value that we imposed before would actually become a little smaller close to the junction. So we would see sort of a fall off in the steady state excess carrier concentration close to that interface. Now it becomes difficult to treat this case fully, but we can take a nice limit. So the so-called short diode limit, instead of this case where the carrier concentration goes to 0 at x equals infinity, let's assume that our surface recombination rate, which again is in centimeters per second, so it's called the surface recombination velocity, is actually infinite. And that means that our delta n of p evaluated at x prime equals WP, the width of the p-type region, has to go to 0. So if we apply that, we end up getting an expression that involves hyperbolic sine functions for the delta n as a function of distance. So let's take a look at that. So I've written here the expression for our excess carrier concentration in the p-type region in the case of a so-called short diode, where this finite width of the p-type region is comparable to or even smaller than the minority carrier diffusion length. So you end up introducing this hyperbolic sine term on the end of the expression. Now, in order to get the currents, of course, remember we're in the region with no electric field, so we would calculate the diffusion current over here, and that's going to be equal to negative d times the charge of the electron q times d delta n p dx prime. So before we do that, let's look at what happens to these functions here in the limit where the WP is actually smaller than ln. So in that case, we can make the small argument approximations for sinh. So in the small argument approximation for sinh, this is about equal to x. So we can then write that this whole term is this argument over this argument. Then we go through and we take derivatives, and I'll leave proving this to the viewer. So at the end of the day, after taking derivatives and doing some algebra, you can show that the J naught for a short diode, in the case where the region on one side is smaller than the diffusion length on that side, is given by E, the diffusion length, the NP naught on the, that's the DN, NP naught on the p-type side, and then instead of a diffusion length, we substitute in the actual physical length of the short region. Now, if you have two short regions, if both sides are finite compared to the diffusion lengths, we add a short expression for both of them. So in the case of one, you would have, so for example, if the p-type side is short, the n-type expression would have Ln appearing in the denominator, but if it's short, you would replace it by Wn. Okay, so this is the current that will flow in reverse bias saturation. And you'll notice that because we've assumed that that WP is less than LP, and similarly for WN, it represents an increase in the current. So for a short diode, we would see more reverse saturation current.